All right, what is up, everybody? Welcome to a little prequel to Chapter 7. Like Star Wars, we're gonna go a little prequel action here. So, um, we're gonna be talking about trig, and the basis of trigonometry is this. We just got done talking about similar triangles, and when we deal with right triangles, we want to talk about similar right triangles and how they progress and what do they have in common, and then how does trig fit in. So let's, for instance, say that I have this right triangle here, okay? And I have, let's say, a 45-degree angle, all right? Or even just 40. Let's pick a random number like 40. A 40-degree angle here, right? Now that forces this angle to become 50 degrees because they have to add to 180, already using 90, so these two angles have to add 90. And let's just say I start stretching and shrinking this. So let's say for our purposes right now, these have a length of 3 and 4 because it's a 3, 4, 5 right triangle, always works. And I know these angle measures won't be exact. They're not going to fit once we get into trig, but just an example here, okay? And let's say that I start stretching these angles out, or the triangles. So if I make this bigger by some factor, okay? Let's say in this case that I triple it. So now I'm getting lengths of 9, and here I'm getting a length of 12. And do the angle measures change is the question, right? Do the angles get bigger? And we know from our study of similar triangles that no, they don't. Okay? These angles have to stay the same because the angle-angle theorem, right? So that becomes the question. And what you should notice here is when you make a ratio of these sides, 3 to 4 and 9 to 12, that they're equal. These ratios are the same. They're both equal to 3/4, okay, 0.75. And this is the common theme with right triangles and similarity, that if you take any right triangle, you can stretch it and shrink it and make it as big as you want, right? I make it as big as I want, that 3 times some number and 4 times the exact number, right? Remember our ratio question? We attach an x onto them, okay? That no matter what you do with those numbers, that ratio of 3x to 4x is always just going to equal 3/4. And so what people started to realize was that as you stretch and shrink these, that these ratios of the sides always remain the same. And so if I'm given a ratio and I knew what it was ahead of time and I recognized it, I can actually tell you the angle measures. And that's how trig kind of works. It uses the ratio of the sides to help you get angle measures, and vice versa. Helps you use the angle measure to then go get the ratio of the sides and find missing sides, which is important. So let's get into the crux of it, which is what is trig and how do we actually how do we look at it and start to recognize the procedure to answer questions. So let's take a look at the first one. In the opening exercise, triangle ABC to the right, we want to name the side opposite A in 2 different ways. And so, before I forget, let's not forget, yes, the frozen placemat is back. All right. So let's not forget here, the side of the triangle opposite A in 2 ways. So if this is A, right, opposite would mean like if I shot, threw a snowball out of this way, where's it going to hit? Frozen theme, right? So it's going to hit this side. So this side, in 2 different ways, could be the length CB, right, that side, or I could switch them around and make it BC. And so those are the 2 ways. So the same thing with B. So what would you do for B then, right? So just shoot a snowball out, right, and see if you can write it down here. All right, hopefully you wrote AC or CA. And we're putting the line over because if we don't, remember that means the length of instead of the actual segment. And the side opposite angle C, this is AB, right, or BA. And we throw the line over it. This pen's not the greatest. So, vocabulary, all right? When working with an acute angle of a right triangle, and remember these right triangles, because this is 90 degrees, These have to be acute angles. Because if the other one was more than 90, right, 90 plus, let's say, 95, you go over 180, which can't happen. And you can't have two right angles, because then that would be 180, and the third angle just wouldn't be able to exist, and we don't have a triangle anymore. So they have to be acute angles, okay, based on the marked angle. So here's a marked angle. So the side across from the right angle, right, the side across, remember, here's our right angle. Man, what is with these terrible pens? All right, going back to the first terrible pen. The side across from the right angle. So like you can draw an arrow to it, right? This side is called the hypotenuse. I'm seriously getting a new pen. Okay. Next question. Fancy. This pen looks fancy. Look at that. All right. The side across from the marked angle. So when you look at the marked angle, the side across from it is considered the opposite leg. Okay. So remember, we have the hypotenuse, which we call HYP for short. We have the opposite leg, which we usually label as OPP. Right, you know me, you know my nature fans out there. And the side next to the marked angle is called the adjacent leg. And that's what we label ADJ. Now it says not the hypotenuse because there's technically two sides that are next to this angle that are adjacent to it. But one of them is the hypotenuse. The other one we consider the adjacent leg. All right. So for each triangle below, label the appropriate sides, hypotenuse, opposite, adjacent, with respect to the marked acute angle. So we have our marked angle over here. It's angle R. So if you want, remember the right angle, just look across. There's hypotenuse, okay? We have next to the right angle, so attached to it, the side that's connected to it, is the adjacent side, that's ADJ. And then opposite, like we shot the snowball out here, right? This is our OPP, that's our opposite leg, all right? And then we have the same thing here. We have a right angle, angle F is our marked angle. Let's see if you can label this one, all right? And hopefully you came up with something like this. Adjacent, right, connected to it, so that's the leg. The other side that's connected is the hypotenuse, always across from the right angle. And then opposite that, there's our opposite side, that's D. All right, very good. Okay, vocab, more vocab. The trigonometric ratios are functions of angle, commonly represented with the Greek letter theta. This is pronounced theta. And it's kind of written like a circle, and then you just kind of make a little squiggly line, like a swoop line through there, okay? Like a bad cursive O, all right? They relate the angles of a triangle to the lengths of its sides. Three basic trig ratios are pronounced sine, cosine, and tangent. And they have the following ratios. The abbreviation for sine, so this is, instead of writing sine, right, theta, they just put SIN. So sin is not pronounced sin, it's pronounced sine, all right? Cos, this is cosine, and the tan is tangent. So this is sine theta, cosine theta, tangent theta. And theta is always referred to when we talk about geometry or trigonometry as an unknown angle, okay? So if you see at A, there's our theta here, okay? That's our unknown angle. So the sine of theta is, and we're going to do this, we're going to remember this word, okay? SOHCAHTOA. So sometimes you'll see it written like this, SOHCAHTOA, or as I like to write it, SO, Ka, and Toa. And here's why. So what this actually represents, and I learned this when I was in your shoes, learning trig too, is the sine of an angle is equal to its opposite leg over its hypotenuse. So SO over H, SOH, so, right, SO over H, okay? We have cosine, which is the A, stands for adjacent leg, over the hypotenuse. And usually when we write this, we just write OPP over HYP, right? That's ADJ over HYP, okay? And then once again, cosine is adjacent over hypotenuse, is CAH. Ka, right? Ka. So there's the ka. And then the tangent, you guess what O and A are? It's the opposite leg. I have to get that far, right? Opposite leg over the adjacent leg, which we usually write as OPP over ADJ. Okay, that's our shorthand version. So if you see writing op over adjacent, right? Opposite over adjacent. So tangent T is opposite over adjacent. So that's the TOA, TOA. We pronounce that TOA. So ka, TOA. All right. And it's just a mnemonic device that lets us kind of remember something using the first letters of the words. So using the triangle picture to identify the following. So the sine of A. So the first thing we're going to do is we're going to find what's called, I like to call this, called the reference angle. This is the angle that we're referencing all the sides from. So when we talk about the opposite side, it's in location to this angle. So our reference angle is theta. The opposite side is over here, and that's BC, or CB. So it's BC over, and it's over the hypotenuse, right? The hypotenuse is across here, and that's side AB. So it's BC over AB. All right, so here's what I normally write when I get to a question. Cosine of A, adjacent over hypotenuse, right? Ka, okay, and now I fill in. So the adjacent side is attached, so that's AC over the hypotenuse, which we know is AB, and we're done. Okay, tangent is TOA, so it's opposite over adjacent, TOA, right? And then the opposite of A is BC. The adjacent is AC. And that's it. There's your ratio. Okay? Which means if we knew the angle measure, let's say 45 degrees or 60 degrees or whatever we chose, that no matter what the size of the triangle is, the ratio between these two sides has to always be the same, no matter what size it is. If we know the angle measure, the ratio of sides has to be the same. Okay? All right, so label the sides of each triangle with respect to the circle angle, which is our reference angle. That's hypotenuse, opposite, and adjacent. All right, so here we go. Circle angle. All right, across from the 90-degree angle is always the hypotenuse. It's a good place to start. Across from the circled angle is our opposite, and then attached to it, the last side is our adjacent. All right, so find the following trig ratios. So the sine of A here, sine, right? And if you forget, so, ka, toa. So, over H, opposite over hypotenuse. We plug in. So the opposite side was CB over the hypotenuse, which is AB. Okay. The cosine of A, right? Koa. Ka. So, koa, what was that? Ka. So that's adjacent over hypotenuse. So adjacent 5, hypotenuse is still 13. Oh, I probably could put the numbers on, right? 12 over 13. Okay, and then the last one is starting with tangent of A. So we go tangent, once again, is TOA. So it's the opposite leg over the adjacent leg. The opposite is 12, the adjacent is 5. So this is 12 over 5. And this is all it is. This is trig, guys. We're doing it. Okay? It's the same thing here. Here's our reference angle. So now when we label, notice that before, when angle A was here, this side was opposite. But if we talk about the reference angle from B, now this side, AC, becomes the opposite. And then adjacent is the 12. So notice what happened here, right? And the hypotenuse, it's still the same side because it's always in relation to the 90-degree angle, which doesn't change, okay? So the sine of B, angle B, once again, is opposite over hypotenuse. So that's 5 over 13. The cosine of B is adjacent, right, over hypotenuse. And so that's 12 over 13. And then the tangent is the opposite over the adjacent. So the opposite over the adjacent. We just fill it in. It's 5 over 12. So the challenge question here is, why is it that the sine of A and the cosine of B, right, the sine of A, why is it that these two are the same? And why is it that these two are the same? And how come these are just like the same thing, but they're flipped? I want you to think about that. See if you can challenge you to see if you can come up with an answer to this. And we'll go over this on Tuesday. Why Tuesday? Because there ain't no school Monday. All right. Okay, last one, and I'll let you guys do this. Use the triangle picture below. Identify the trig ratios. So what I want you to do is try this on your own. Okay. And I will post the answers to this on my teacher page. So if you want to go there, you can figure this out. All right. And you can check it later. All right, guys. Have a good weekend. Enjoy yourselves. Stay safe. Stay warm this weekend. It's supposed to be kind of nasty out. So, all right. Don't get frozen. Oh, man. I'll be here all day.